Welcome back to eCoreAcademy, everyone. My name is Anita and I am the co-founder here along with my younger brother AJ Raj. We're going to be continuing our Algebra 2 course with this new lesson on transforming polynomial functions in our polynomial functions unit. We're going to be moving right along with the topic here, where we're going to have a focus on graphical features of polynomials that you'll encounter in Algebra 2 and maths that are more advanced that go beyond the scope of this course. So the objective in this lesson today is going to be applying transformations to graphs of polynomials. What do we mean by this? Well, every kind of polynomial function family, you can think of it that way, has a parent function. For example, y equals x squared is the parent function of quadratics. Y equals x is the parent function of linears. Y equals x cubed is the parent function of cubics. Y equals the absolute value of x is the parent function of absolute value equations and functions. In such a way, we can alter this parent equation so that when we look at the new or transformed equation on a graph, it looks a bit different. It could be shifted horizontally, shifted vertically, stretched, compressed. All these different features can be changed if we apply transformations. And we're going to be in this lesson specifically looking at transformed equations and being able to literally translate what has happened to the graph into words without having to look at the graph, so that when we actually maybe have to graph this polynomial, we have an idea of what it's going to look like compared to the parent function, which we should be familiar with. We'll also go in the other direction where we're going to be given verbal, in words, kind of instructions and descriptions of what a transformed function looks like, and we're going to translate that into the equation of an actual polynomial. So that being said, before I get into the lesson, I would really appreciate it if you all could subscribe, hit the post notification bell, and drop a comment down below. Please also share using our socials, and let's get right into the lesson. Here's problem number 1. In this lesson, we're going to primarily be looking at the cubic function family, and if we're looking at cubics, the parent function is going to be y equals x cubed. It looks almost like a squiggly line that passes through the origin. You can also I think of it for some reason as having hips at the origin, but at this point, hopefully you're familiar with that. And what the purpose of this problem is to identify some transformations that are going to be done to this y equals x cubed parent function. In this first scenario, let's say we were looking at y equals 1/4 x cubed. Well, we still have the y equals x cubed, but we've just thrown a 1/4 in front of it. So what does that exactly mean? Well, in this case, 1/4 acts as a coefficient. I would think of it almost like y equals ax cubed, and a is a coefficient, and in this case, a equals 1/4. Whenever you have a coefficient like this that's between 0 and 1, what happens is that the graph, if you look at it vertically, so if you look at it up or down, neglect the horizontal features, just look at it up or down, it's going to be almost like squished downward. So if you're looking at a parabola and we had a value between 0 and 1, so you can think of it as a fraction, it's going to be squished. You can almost think of a parabola. Let's say you put your hands above and below it and you just squish it. So it's going to be a little bit wider. You can also think of it as if you had a linear equation. If the slope which is m, was between 0 and 1, the slope's going to be more shallow, not as steep. Think of it that way. You're almost squishing the graph. So you're going to have a vertical compression. That's what we say that's how we express it mathematically. We don't say the function was squished, obviously. We say if the coefficient is between 0 and 1, in this case it's 1/4, which is the fraction, which is between those values, we say it was vertically compressed. Compressed almost means squished or contracted by a factor of 1/4. We always include what the factor was, so by a factor of 1/4. In this next example, the complete opposite happens because we see that the coefficient is now 12. 12 is over 1. 12 is much greater than 1. And what happens is if our coefficient is over 1, it's going to actually take the graph, and rather than squish it, it's actually going to pull it vertically. So you can think of a parabola that looks like this. If we have a vertical stretch, what happens is we actually make it skinnier, if you want to think of it that way. We pull it upward more. That's how I think of it. So we're going to that's called a stretch in math. So we're going to call it a vertical stretch, and it's by a factor of 12. So we always include by that factor, and then we just write the coefficient after that. So vertical stretch by a factor of 12. Next, we have y equals negative x cubed. So in this case, our coefficient, you can think of it as -1. But I haven't mentioned negative numbers yet, so what exactly happens? When you have a negative number, what happens is that there's going to be something called a reflection over the x-axis. So typically, functions have the normal parent function. They look a specific way. Parabola opens upwards. It's concave upwards. In this case, a cubic, I can kind of show you with my hands, but it's oriented a specific way. When we say negative, we're pretty much just flipping it the other way. So if we want to think of a parabola, we almost flip it over the x-axis. So if it's upward, it's concave up. If we put a negative in front, coefficient of -1, we flip it over the x-axis. Same thing with a cubic. If it's oriented a specific way, when we put a negative, it's flipped the other way. So you can actually, that's how you can actually think of it when you have negative coefficients. Now we have y equals x plus 7, that whole expression cubes. We don't just have an x cubed anymore. We're throwing a plus 7 and we're cubing that whole expression. So what does that exactly mean? So think of parabolas. Think of vertex form. Y equals a times x minus h squared plus k. Whenever we throw a value into a set of parentheses with k, this is going to result in a horizontal shift. So a shift along the x-axis horizontally. Think of the horizon, the sun rises there. So whenever you have a set of parentheses, that immediately indicates a horizontal shift. Typically, we'll see x minus some value h. So this should be a minus sign if the h value is positive. But since here it just says plus, it's actually the opposite. So always think opposites. If this was, for example, x minus 7, that means we're moving right 7. We're moving in the positive direction. But since this is x plus 7, that means that the value originally here was a -7. X minus -7 is equal to x plus 7. So in this case, it's actually a -7. So we're going to move left 7. So always think opposites when you have scenarios like this. So that's why it says shift left 7 units. So if you just say left 7 units, it's sufficient enough to say it's moving horizontally, it's moving left 7 units. Now we have a little bit different of a scenario. Now we have y equals x cubed minus 5. So we don't have the minus 5 in a set of parentheses with the x. We just have that following the x cubed. And what does that mean? Well, think of that as like the k in your vertex form of a quadratic equation. The k value is going to move it up or down. So it's going to be a vertical shift, up or down. So in this case, if this is a bit more straightforward, it's not like the opposite sign thing that we went over in the last example. If it says minus, you're moving down you're moving in the negative direction of the y-axis. If it says plus, you're moving up, so in the positive direction of the y-axis. So since this says -5, you're simply going to shift your parent function down 5 units. And that's how you would express it mathematically. So let's jump right into, I think we're going to go to problems. Yeah, parent function is still going to be y equals x cubed. We're going to continue to identify some transformations with this. I'm trying to keep the same y equals x cubed function. I'm not trying to use y equals x squared because we've worked extensively. We had a whole unit on that. So let's try to get more comfortable with other polynomials. That's why I wanted to use y equals x cubed. So enough of me talking. Let's jump right into this example. So let's say we're given, I know the answer is up here, but just go along with me for a second. Let's say we're given the equation y equals -2 x plus 1 cubed minus 4. You can see it up here. So we have this long equation. It almost looks nothing like the parent function other than it has a y and it has an x cubed. But trust me, it does have quite a resemblance. It just has a few transformations done to it. Specifically, it has, you can say, 4 transformations done to it. So what I would do is when, in these cases, you're going to be given an equation like this, and your teacher might ask you, okay, identify every transformation that's been done to the parent function to give you this new function here, you can think of it as the resultant function. So in that case, I would always start with the coefficient. In this case, it's -2 because it comes before whatever the x cubed term is. In this case, it's in a parenthesis. But we have a -2. If we have a negative, like we said, it's going to be reflected over the x-axis. And we have 2. 2 is greater than, I would think of the negative and the 2 as two separate things, and then you combine them in your description. So the negative implies that it's reflected over the x-axis. Then we look at the 2. 2 is greater than 1, so that implies that there is going to be not a vertical compression like that. It's going to be a vertical stretch because you're pulling it because your factor is greater than 1. So you're going to have a vertical stretch by a factor of 2. So make sure you mention the by a factor of 2. Then we're going to look at inside the parentheses because this will indicate a horizontal shift. We have an x plus 1 here. If this was a -1, we would be going right 1, but this is a plus 1. So we actually start with a -1, so x minus -1 is equal to x plus 1. So we're actually shifting left 1 unit. So think of opposites. And then lastly, we have our vertical shift because it's outside the parentheses at the end. We have -4. That's pretty straightforward. -4 is just shifting 4 units downward. And that's how you would describe a translation of the parent function. Next, we have next in this example, we're actually given a description of what the translation's like, and we have to write it as an equation. So we have the equation of the graph y equals x cubed, and that's the parent function of a cubic, so that's what we're going to be working under. We're doing this under a vertical compression of 1/2. So the factor is 1/2, and we're putting this as the coefficient. So that's going to be coming in front of x and whatever else mumbo jumbo is going on with the x cubed. So that's going to be, think of it like our a term, the first thing that shows up. And it doesn't say a reflection over the x-axis, so it's going to be a positive 1/2. And the factor, again, is 1/2. So we put y, I wrote it down here, actually, y equals, let's start off with the 1/2. And again, another indication, if you weren't sure, this is vertical compression. Compression is when the graph is squished, so you're looking for a coefficient between 0 and 1, and 1/2 is a fraction that falls in that range. Then we have a horizontal translation, 7 units to the right. So when we think horizontal, this is going to be going in a set of parentheses, excuse me, with the x, and then that set of parentheses or that expression is going to be cubed. So in this case, this is horizontal translation, 7 units to the right. So we're moving in the positive direction, so 7 units right. But we write it in the equation, we're going to write it with the opposite sign, because think we're doing x minus some number h all cubed. In this case, h is 7, which is positive, so we're going to write x minus 7 cubed. And then lastly, for the vertical translation, 2 units up, we're moving in the positive direction, so we're just going to add a plus 2 to the end. So now let's move on to another problem. This time we're going to be finding the zeros or the x-intercepts or the solutions or the roots, whatever you want to call them, of a transformed cubic function. So we're pretty much finding where does this cubic function intersect the x-axis. So we're given the problem if a, h, and k are real numbers and a does not equal 0, so a is some value, how many distinct real zeros does y equals negative a times x minus h cubed plus k have? If you recognize vertex form for a parabola, you can almost think of this as the equation for the transformation of a cubic function. Just because you see a cube here, it looks a lot like vertex form, except we have a cube here instead of a square. So if we have this equation right here, how many real zeros does this have? Think of it for a second. We're not actually trying to find the specific value where this intercepts the x-axis. Why? Because we're not given actual numerical values for variables such as a, h, and k. We're just given these variables, so we're almost doing like a literal equation, if you remember those from Algebra 1. So what we want to do is to find the distinct real zeros. What we do is we always set this equal to 0. So we're going to do 0 equals negative a times x minus h cubed plus k. And remember, we're solving. Think of it. What are we solving for? We're solving for x because we're trying to find what value of x gives us a y value that's equal to 0. So we're trying to get x by itself. The first step you should do is subtract k from both sides. So you get negative k equals negative a times x minus h cubed. Then what I do is divide both sides by negative a, so that you can get this x minus h cubed by itself. So you get negative k divided by negative a equals x minus h cubed. Then what you want to do is get rid of this cube, so you do the opposite, which is cube root both sides. That's why you see k divided by a raised to a 1/3. Remember, negative divided by negative is positive, so that's why we have the positive k divided by a. It's the same thing as negative k divided by negative a. And that's going to be equal to x minus h. We're going to get rid of that cube because we did the opposite function. Then what we're going to do is we're going to add h to both sides to get k by itself. So we get x equals k divided by a to the 1/3, so cube root of that plus h. And this would give us one distinct real zero. Because if we plug in values we'll be given values for k, a, and h, the numerical values in a normal transformed cubic function. And if we use those, we can figure out the one distinct real zero in this case. So problem number 2, finding zeros of a transformed cubic function. Same theme, but a different situation where we're actually given values for a, h, and k. So what are all the real zeros of the function y equals 3? This is our a, k minus 1, 1 is our h cubed plus 6, which is our k. And again, we're just going to set this equal to 0. So 0 equals 3 times x minus 1 cubed plus 6. We're trying to get x by itself again. So we're going to subtract our k value, which is 6, from both sides. So negative 6 equals 3 times x minus 1 cubed. We're going to divide both sides by 3. Negative 6 divided by 3 is negative 2 to get the x minus 1 cubed by itself. We're going to do the opposite. And I'm sorry, I don't know why this says to the 1/2. It should say 1/3 because we're cube rooting it. So negative 2 to the 1/3 is equal to x minus 1 because the cubic cancels out. And then if we add 1 to both sides, we get x is equal to the to the cube root of negative 2 plus 1, or if you factor out that negative 1, you can actually rewrite this as 1 minus 2 to the 1/3. You're not actually factoring it out, you're pulling it out of the cube root. So you can write that answer either way if you did the work for this problem. And that's all I have for you today. I hope you enjoyed the lesson, and if you did, please like, subscribe, and hit the post notification bell. Please also drop a comment down below and share using our socials to help promote our platform. I'll be back with a new Algebra 2 lesson soon. Thank you for sticking around for our educational videos, and I'll see you next time. Bye!